what dynamic and nonlinear terms should be in the final model. What are the most important terms in this 18,000? So we use the Froll's algorithm, which is actually the forward regression orthogonal least square algorithm, in order to determine what are the best terms in the NARMAX model for our case, for our system. So according to the Froll's algorithm, we determine the following terms, which are actually 7. No? And with that, we start, well, to be honest, in this part, to describe the process that we performed before, we need to use it first of all, the NARCS model in order to obtain first the errors. And then we use the NARMAX model to complete the terms that we need for our system. Okay, so we have in this part the terms necessary to represent our system, but also we need the coefficients of the model, the parameters. In order to estimate the parameters of the model algorithm, a recursive least square algorithm, to determine the parameters of the model, and then we have the, well, in this part we can say that the identification is complete, but also we need the validation of our system. In this part we have the response, or well, in the real distance, the distance modeling using NARCS, sorry, and then that is the modeling using NARMAX. Well, in this case, the figure shows a little difference between those, between these systems, between these models, sorry. Okay, but also we need to complete the validation of our system. We have the autocorrelation. Well, sorry, we use the cross correlation proposed by Billings in his papers, to determine if the model obtained is valid for our active magnetic invariant system. No, the central concept in this case is that the residues of our model must be unpredictable. So we need to establish certain bands of confidence bands of 95%. diminish the stability, the instability of our system, and also control the deviation of the shaft. Well, that is all. Thank you for your attention.
Thank you very much, Mr. Manzano. So with that, we will go ahead and take some meaningful questions. So anybody can make a question and you can write that in the chat box. Okay, so we have one. It says, where you can apply this type of technology more frequently.
Where? Sorry, is where the question?
Yes.
Okay. Well, in this case, the use of identification NARMAX, well, non-linear identification using NARMAX or NAX model is recommended, especially for non-linear systems which have which are difficult to linearize. No, in our case was the active magnetic invariant system, because we know that magnetic systems has non-linear uh, non-linear functions, so it's difficult to work in linear controls or linear identification with this kind of system. But if you have the opportunity to use it with other non-linear system, yes, is well, it's actually is recommended.
Okay, thank you. Yes? Does anybody else have another question? Okay, I think that we can continue with the next presenter.
Okay, thank you so much.
Okay, thank you so much. So, okay, we continue with our session. Our next presenter is Herman Moreira from the Polytechnic School of the University of Sao Paulo in Brazil. He will present the paper number 11 entitled Application of Demand Response on Smart Grids. So now, Mr. Moreira, the floor is yours.
Yes, I'm here. Thank you so much for this presentation. And okay. Can you see my presentation? All right.
Yes, I can see.
Okay. My paper is entitled Applications of Demand Response on Smart Grids, and I'm a first author, Herman Leal Moreira. I'm a PhD student at the University of São Paulo in Brazil, and I'm professor too, and another institution. And the second author is Dr. Nelson Kagan. And this work is about a project that we are developing in our institution, and we have I would like present this model that we are working now. That's right. In this introduction, I would like present to yours that the physical integration between end users of energy or consumers of energy and the power grid operator uh, can provide many facilities and opportunities to restructuring power electric system using technologies like data analytics, big data, IoT devices, cloud computing, and another new technologies. All right, and this is an opportunity to apply at the conventional power electric systems. Our work propose to develop a system that can integrate and prove benefits of logical and physical interconnection, demand response utilities, integrating the concept of smart cities, smart grids, smart demand response, smart building, and smart energy, integrate smart generation and smart end users, right? Uh, what the benefits about this? First, we have a more reliability. We have to energy efficiency. We can provide new scenarios of residential and commercial microgeneration on prosumers, and available data to use in planning and operation of the grid. That's right. In the figure 3, we have a demonstration or an illustration about this type of integration. At here we have, for example, renewable energies. At here we have a type of storage system that can use batteries or another type of storage. We have diesel generators, and this these renewable energies can be integrated by an inverter, and we can use to electric vehicles to integrate in a small consumers or commercial consumers, and we can apply to this model to industrial consumers. That's right. Um, to apply these new technologies like data analytics, cloud computing, IoT devices, for example, big data, we can use microcontrollers to control the end users, right? End users and the load into the residential or industrial consumers. This data obtained in this site we can send to cloud computing, right? And with these data we can apply data analytics and obtain load shapes, and these load shapes can be sent to distribution operation centers. With this data and with this analysis, the operator system can use big data techniques to planning and the microgrid of the smart grid. This is the main difference between conventional energy systems and new energy systems like smart grids. All right. Well, our background is based on demand response that can use and provide connect objects by internet, remote monitoring of these loads, multi-operation by IoT, adjusting the load curve at here, this figure. We have an adjusting load curve in the period of peak demand, and control loads via DR, demand response, all right? And for example, if we have some consumers like residential and commercial, these loads can be controlled about IoT devices. And the smart grid promoted power utilities, new service models, more participation providers in market, distributed generation and energy store integration. That's right. And active management system applied to smart cities. The big data technologies can collect and store data regarding the consumption and generation and energy storage. We can provide with this data mining, analyze and generation, produce profile demand curves, right? Our method is based on intelligent dispatch of energy model developed, right? I study, for example, I study platform of simulations is proposed in another work, this reference 4, And centrally, the intelligent system uses a distribution feeder test with the idea of information from other systems of the energy companies, such as GIS and SCADA, and use of complex calculations of the network, such as state estimation, power flow in small networks, with less than 135 buses, right? In which the calculation of power flow requires less computation cost. Our model was implemented using the ER, right, the demand response techniques, and the concept of smart grids. And we create a model of platform that was developed to perform an intelligent dispatch integrated prosumers, aggregators, network operators, energy market agents, using a set of possible network planning and operation scenario, as we'll see ahead. Well, this figure presents the intelligent dispatch of energy model developed for us. And first, we have at here renewable energies, right, and storage systems, and we have conventional energy resources. This data of this type of energy can be controlled and measured and to measure, and this data will be sent to a hub, like a hub, right? And this hub will be controlled to IoT devices. And we have, for example, the level of generation about photovoltaic solar photovoltaic energies, wind energies, thermal, hydraulic, and this data will send to this hub. And for example, if you have a power plant or a site and that we have this type of installation of renewable energy, we can control the production of energy, and with data analytics, we can use this data to choose the better local or the better time to dispatch this energy. All this data will send to cloud computing, and we have a connection with these consumers by IoT devices too. All right, and for example, we can choose the type of prosumers, rural, industrial, commercial, or residential, and if it's possible, we can optimize the dispatch by demand response. We will proceed this type of control. If not, we will try the conventional dispatch. The next figure show how can it proceed. For example, the method of our intelligent dispatch model, we use direct load control, for example, right? And if you have installed in the residential consumer type of direct control by IoT, we can optimize this dispatch by demand response. If you know, we have a conventional dispatch. The next step is dynamic rating, is about the price of energy. If you have another type of tariff, all right? For example, in Brazil, we have a white tariff. We can dispatch to this energy by direct load control and white tariff, right? And the next step is to simulate the grid if we have a good performance about voltages, about currents that flows by the grid. Okay, and finally, if in the last step we have direct control, white tariff or dynamic rating, we can optimize the balance sheet and to finally this dispatch, this intelligent dispatch. Well, the optimization proposed method is based in linear programming, right? And first, we can to minimize the use of consumption or purchasing of high cost energy, or to maximize the profit or sale of produced energy, like production or sale, right? The objective function formulation is based on the first cost for acquisition, deployment and return on investment of the power and solution, control technology and your restrictions. The second point of our objective function is about the investment in low voltage and medium voltage grids of the power companies and your restriction, including power losses. And the third part of our objective function is the equalization trade-off of operations, building and selling between consumers enjoyed in accordance with performance of the actors involved in the order maximize their earnings to minimize your loss for the execution of the contract based on tariffs. At here in this figure, we have an example for these three parts of objective function. The first part is about to minimize or to maximize, and we have this side, all right, of the optimization. The second side is about the optimized dispatch, like minimization of production, of consumption. The third part is about rating, all right, is like tariffs. And the last one is about the network infra, the viability, the available use of grids. I think here we have.
I'm sorry, 2 minutes to finish, please.
Okay, thank you. We have an architecture solution proposed. All right, is like a hub that interconnect our prosumers and the grid. We have the input data at here, right? We have a key. We have here data acquisition about network operation center. We have here a microcontroller, and the consumer or prosumer can insert it your demand or your data about a tablet or an app, and here this data is concentrated on cloud computing. We have here an artificial intelligence about a program, and we have the benefits of the model response at here in this last part. Finally, our contributions is involves the logical and physical integration between hardware devices and software applications by IoT and big data. We can use techniques of machine learning, data mining, and analytics, and the model and platform was developed to available visualization and interpretation of the characters of consumption, logic curves of generation, storage, and the timely information for decision making, multivariate analysis. Our focus too is the project involving Industry 4.0 and IoT of Brazilian Ministry of Science and Technology. And another objective is enables the control and acquisition of data in real time for validation routines and simulations that will be dedicated to new features utilities and simulation tests of electrical distribution networks with a focus on DR in the form of prototypes at the University of São Paulo, all right? And the proposal model and your test platform contributes to studies on the implementation of new tools and technologies to solve typical problems of automation. In addition, the work proposed application of new technology integrates the various sectors of electricity supply chain. And finally, the discussion introduced a proposal for innovation to conventional electrical systems by bringing an approach focused on the use of renewable energy sources. I'm thankful for everything. Thank you so much.
Thank you so much, Mr. Moreira. So we will go ahead and take some time for questions. Does anybody have a question? Please write in the chat box.
Sorry, I can understand. Could you repeat, please?
Yeah, we will take some time for questions.
Yeah,
So
I have.
if anybody only 5 minutes or maybe depend the question that people can write in the chat box.
We have a question here in the chat.
Yes.
What is that?
Yeah.
Can I answer?
Yeah, of course. First, I'm going to read the question for all the people that wants to listen. So, what is the advantage for distribution business that can apply demand response?
All right. This discussion is the main discussion about our dam. All right. And for example, we have two sides: the side of consumers and the side of companies. All right. The great opportunity for companies is that the companies can install it, renewable energy sources and many local sites of the grid, all right? And the company can use this same controls to operate the grid. For example, if the company have a site and we have a bank of batteries, the company can use energy to storage for the period of intermittence of energy solar, like a period of the day, and the night to dispatch this energy in our peak demand, right? And this type of control can provide a better performance to the grid.
Okay. Yeah. So the next question is, who is going to pay for the infrastructure?
Well. This type of investment first is paid to the prosumer of consumer, but in Brazil and in the other countries we have the contribution of the government. All right, we have policies about the government that start these initiatives to renewable energies, to apply renewable energies, like resources in a bank or financement and other types of investments to apply this infrastructure.
Okay, thank you.
In resume, this investment can be public or private.
Okay, thank you so much, Mr. Leal. So let's continue with our session. Our next presenter is Ismael Sanchez.
Okay.
Okay, thank you so much. From the
Good morning.
Yeah, from the Universidad de Piura in
My
Peru.
content.
Yeah. I'm going to present you. He will present the paper number 31 entitled Using Weather Prediction in a Grid for Efficient Regional Wind Power Density Forecasting. So, Mr. Sanchez, the floor is yours.
Okay, thank you very much. This is a joint work with Miguel Garcia Lobo. Miguel Garcia Lobo is working in Spain in a large electrical company, and I'm working at the university. I'm engineering, but I'm the expert in statistics. Okay, I'm going to talk first about the necessity of having good predictions in energy. Then I will differentiate between the classical approach and the approach that I'm proposing here. Then I will compare my approach with the alternative. Okay, why do we need wind power predictions? Okay, wind power is a non-dispatchable energy. The owners of wind farms, they cannot offer to the market the energy that they want. Also, the transmission system operator cannot use as much energy as they need from this kind of wind power energy. So it's very difficult to balance, to equate supply and demand. Therefore, it depends on the variability of wind, which is a stochastic variable. And also, in many cases, the wind has a high variability that can provoke important problems, even though the system can accommodate some fluctuation. Then, traditionally, all the agents, transmission system operators, on utilities, has their own forecasting tools to predict the energy that they can supply in the next time. Why do we need regional wind power prediction? Okay, there are different agents that need the regional different prediction. Regional in compared to individual wind farm power prediction. Okay, the system operator has to balance the whole system. In countries with high penetration like Spain, Denmark, or Germany, it is critical that the transmission system operator has a good predictions to manage all that energy. So they can make efficient schedule and reserve or identify potential bottlenecks at some nodes. But also utilities need regional power provision because many of them are large companies that has wind farm in different point of the geography. So they want to know every morning how much energy they have to attend the market in the countries that there is a market, like in many countries of Europe or other states. Also, they can optimize their strategy. For instance, if I know that I can supply this energy with a 90% of probability, then I can keep this energy for a secondary market. Also, they're going to be penalized if they fail to supply the energy. And the penalized is not for the error in individual wind farms, so by the aggregate level. So both system operator and utilities need aggregate efficient wind power prediction. What is the classical approach? Okay, the classical approach is to make wind power predictions. I'm talking about hourly wind power predictions. Every hour you build a prediction of the power or the energy you can supply, mostly for 24 to 48 hours, up to 1 or 2 days ahead. Then you have to build wind power prediction for each isolated wind farm. I'm going to explain briefly now how to do it. And then we just add them up. We add them up. The predictions is this with hub. And this sum is your regional wind power prediction. What do I, for each wind farm, how do they build the wind power prediction? Okay, there are many methods, but basically can be explained with this picture. So we have here in the x-axis the wind speed. So for efficient wind power prediction, you need the information of the wind speed. You need good wind speed predictions, hourly and updated as much as possible. And the y-axis you have the actual production. Actual production is easy to have because utilities are paid for that information, so it's information of very high quality. So here we have a plot of points. Each point is the energy generated at each width speed. Then we have there some nonlinear function that, depending on the technology or how large is the width range, that clouds easier to model or more difficult to model. And there are many alternatives to convert wind speed or wind speed prediction into power. Probably you can use a neural network. Non-parametric regression is the technology that I'm more used to do. Visual linear regressions, dynamic Rmax. There are many procedures. So in order to perform wind power prediction at wind farm level, we need the history of production and access to wind speed prediction. So, well, what do we propose? What we propose is to obtain the regional wind power predictions directly, without having to predict individual wind farm, because in that step you are committing an error. So you add them up, you are aggregating errors. Also, we not only avoid predicting any individual wind farm, but we also supply not a single point prediction, but a whole distribution, like you see in this chart. You see that the red line would be the, let's call it, point predictions, a single number about how much energy you are going to supply in the next hours. But you can provide this production with 80% of probability, or there is a high probability that I cannot reach even some minute. So you can manage the risk and you can have better bets or better strategies if you can build those predictive distributions. So how do we do it? We are going to use the same information that the individual wind farms. So we don't know additional information. That is very useful, for instance, for the transmission system operator or for large companies, because probably they want still to build the individual wind farm predictions, but also at the time they need the regional wind power prediction, can use more efficient approach. We need the wind speed at some selected coordinates, and the same as you use for isolated wind farm prediction. And also you need the history of aggregate power production. That's information that the system already has. Okay. Also, there are statistical techniques to select the best choices for obtaining the wind speed prediction. Okay. Look at the hand is. Once you have a given point, you have access to a new vector of wind speed prediction. Your meteorological agency that tells you, okay, for 3 hours ahead, the wind speed prediction for your coordinates are this vector. So this is my input, the vector of new wind speed prediction. Then I compare it with my history of vectors, those coordinates of wind speed prediction, and build a distance. Also, I have the historical power, so I can see which power are closer to my vector of wind speed prediction. So we can make up a distribution of power. But also, many agencies, or also the transmission system operator, has already regret prediction, and with the procedure, what you build is a distribution to add to your point prediction. So in the history, when you have wind speed prediction closer to yours, you used to have those predictions and those prediction errors. And what I will do is to build a density using non-parametric methods that are seen in this equation. In this case, the kernel that tells us the density for each point. So at a given point, for instance, where is my hand, I build the density, and this kernel what do is to look for how much prediction errors are closer to that point. If there are many information around that point, the density is high. If very few historical data around that point, the density is low. So this kernel is going to tell how much dense is a point. Then for each point, I'm going to weight with this information. First, I'm going to weight with how old is that information. I'm going to downweight with the time. So older information has less weight in my predictions, and more recent information has more. And is the distance that appears here of the new vector compared to the vector of historical information. So by doing this, I can make a prediction distribution where more recent information has more weight. Information that are closer to my new vector of Winner prediction has also more weight. I'm going to compare this approach with some other approaches. All are based on non-parametric expression, but with different level of information. See the benefit of using the coordinates, the speed prediction at those selected coordinates. My first competitor would be the unconditional distribution. By doing so, the KDAU, I'm telling that the prediction distribution is going to be the same always. I'm going backward, more or less in this slide. Always the prediction error has the same distribution. And with this equation, I'm going to make that model. So the shape adapts to the historical data. Second competitor will be the same, but I'm going to put a weight depending on how old is the data. So I have an unconditional distribution, but more recent data has more weight. So that distribution can have some ability to adapt to time. The third one is very common in the wind power industry, is also to weight the information depending on how close are the historical data to your prediction. I'm going to pass to the next slide to explain that. Because it is known that depending on the level of the predictions, expect level of production or low level of production, in the average, the shape of the distribution is going to at extreme. The wind is very low or very high. The production is asymmetric, positive or negative, and with low variance. And in the intermediate zones, distribution is more symmetric and more dispersed. So the shape of the prediction error distribution depends on the level of the predicted value. And this expression here to put that into the computation. So the density error is weighted by how close are those historical data to your prediction and how risky is that information. Here I have built two competing predictors depending on the bandwidth. Depending on the bandwidth, is a parameter of the non-parametric estimation is fixed or varies. So I have these four competitors where only mine is conditioned to a whole vector of wind speed prediction. Then I'm going to show you how to compare. First, I'm going to compare what is calibration. Calibration in density function means that if you say that something is going to happen, for instance, 30% of times, then in the data I have to observe 30%. If that happens, those histograms here that are called probability integral histogram is going to be uniform. These histograms have been made with data. I've used 2 years of early data, 1 year for the estimations, and the second year for the evaluation. So I have estimated all the parameters needed in 1 year, and then in the second year, I made the evaluation and constructed this evaluation measure that you see here. But you see that the unconditional distribution is not calibrated. When you allow for some downweight according to the time, the calibration improves quite a bit. This RMSE is a measure of how far from uniformity is the histogram. The three histograms below, you see the conditional distribution, and you see already the uniformity is much better. And the best is with the predictor that I'm proposing. We add very well to the actual probability. And these other three measures have to see how time is your prediction distribution, how well they adapt to the current situation. The first one is the sharpness. The sharpness means that if your prediction is very good, your distribution is good, your prediction error has to be narrow. Then a given interval has to
I'm sorry, 1 minute to finish, please.
Okay, thank you very much. So here, the lower better. So the lower, the narrower intervals for a given coverage is obtained by my proposal. The second one is very important, is the resolution. That is going to tell us how time-bound is your distribution. Not always narrow, but sometimes narrower, wider, trying to adapt. Here, the larger, the better. And see here that the larger resolution is attained with our proposed model. This third graph is an overall measure of the quality of the prediction, of the density prediction. And here, the lower is the better, and the best results are obtained also with our proposal. And that's all. If you have questions, I'm ready to answer them. Thank you.
Thank you so much. So now we will go ahead and take some time for questions. Does anybody have a question? And you can write in the chat box. Okay, so I think that we have one. Okay, I think that we have one. Where do you think you would be most likely to implement this technology?
Could you repeat, please?
Where do you think you would be most likely to implement this technology?
Okay, these algorithms they can be very easily implemented by large wind farm owners and also the transmission system operators, because all of them has already the system to handle the data. And probably they have some more or less naive or complex tool to forecast individual level. So all those companies can in fact, this algorithm is already implemented in Spain for Eléctrica de España, the transmission system operator, because my colleagues and myself were building the forecasting model that they are using. So this is based on a real case, and it's already running in real time.
Thank you so much. Thank you so much, Mr. Sanchez. So let's continue with our session. Thank you. Okay, our next presenter is Juan Muñoz from the Pontificia Universidad Católica de Chile in Chile. He will present the paper number 53 entitled Empirical Quantification and Uncertainty Assessment of Carbon Dioxide and Particulate Matter 2.5 Emission Factors of Power Plants in Chile. So, Mr. Muñoz, the floor is yours.
Okay, thank you very much. Good morning to everyone. I don't know if the presentation is showing. Everybody can see the presentation.
It is maybe in. Okay, yeah. Right now I can see. Okay, continue, please.
Hold on. Let me check. Okay, well, basically, I'm going to be presenting the paper entitled Empirical Quantification and Uncertainty Assessment of SO2 and PM2.5 emission factors of power plants in Chile. This work has been done for power plants above 50 megawatts, which is regulatory mandatory in Chile for this plant to register these pollutant emissions from these cases. And this work has been done in collaboration with the colleagues from the Universidad de los Andes and from the Universidad Católica de Chile, University of Chile, and the Solar Research Energy Center. First, we're gonna be going through the outline. I don't know if it's here. We have some problems. Okay, now I have. Okay. First, we're gonna be discussing a brief introduction regarding our research topic. Then we're gonna explain what are the available methods for estimating emission factors in general. Then we are gonna be explaining the methodology that we use in this paper to obtain this emission factor. And then we're gonna be discussing the results and discussion of this and the main conclusions of this work. So why do we need to estimate emission factors, and in general, why do we need to quantify emissions? Basically, we need to have a accurate estimation of emissions to help us to build appropriate mitigation control strategies, so it's very important. To conduct trend analysis to estimate how these emission factors and how these emissions are going to increase or reduce in the long and mid terms, and also if this is linked with the prediction of future emissions, and in general to develop models that can be in the long term or in the medium term or even in the short term to evaluate the impact of these contaminants on the environment in general, and also for building policies in general to help mitigate these emissions from these polluting gases. Also, for real-time air quality determination is very important to have a very good estimation. Recent studies have shown that a long-term exposure to NP2.5 can be linked to an important increase in the number of deaths from COVID-19 in the US. So very important because it's affecting everything in our life. So how can we estimate these emission factors? Well, we can estimate these emission factors by different ways. I just want to explain a few of them. We can estimate the emission factor using hardware-based analysis, which basically samples the emissions from these generators and then analyzes these gases, and then it obtains what is the composition in terms of pollutant and contaminants from these generators. And this kind of system is called CMS, which are basically hardware-based. And we also have software-based equipment that are basically the PEMS, Predictive Emission Monitoring System, which basically do the same thing. This analysis can be used to monitor and also record storing this emission factor from different equipment, and it's not only applied to generators. So this is one way to do the emission factor quantification. And also, some agencies around the world, some international agencies, has taken this experimental values of emission factor and they report in different databases. For example, the Environmental Protection Agency of the USA, or EPA, basically has a very good database where you can find different emission factors from different type of equipment and under different conditions. So they point out that the emission factor presents a high variability depending on, for example, atmospheric conditions, and even for the maintenance of the machine affects a lot this kind of emission factor. So they point out the fact that they give this emission factor as a reference, but that is better to have local measurement to better obtain this emission factor. In Chile, there is a Superintendence of Environment of Chile who also provides some databases where you can get these emission factors. And mostly these emission factors are based on the EPA, so and other ones are just adapted that have been modified with the local conditions. So what we did in this research, right? Basically, we have this measurement from different power plants in Chile, and these power plants are rated above 50 megawatts. So we get historical data from measurements of emissions of these machines in order to quantify this emission factor and also compare this emission factor with respect to the ones provided by EPI or SMA. We also quantify the uncertainty and variability of these emission factors, taking into account individual plants, so measuring each individual plant, and also taking these plants as an aggregate. So we group these plants depending on the fuel source, and we also estimate this emission factor in terms of aggregate model. So we also build linear and non-linear predictive models based on basically what are the parameters that mostly are correlated to this emission factor. So this attempt to build this linear and non-linear models are, let's say, a good input for models that can be used, for example, for determining capacity expansion with some emission targets. So depending on the application, we can use linear or non-linear models, and of course the computational cost that non-linear models involve. So what was the methodology that we used in this paper? So basically, first we gather data of emission of power plants obtained through SNIFA. SNIFA is just an organization that depends on the SMA of Chile, and they have a lot of data, historical data about emission factors. So we basically take the data from 2016 and 2018. And this data was basically composed by fuel type consumption, depending on fuel type. It was organized according to fuel type consumption, power dispatch, concentration of SO2 and PM2.5, the ratio of the amount of fuel and the power dispatch. So you have a lot of data. You can only take the data that we were interested in. And we then use the bootstrap method basically to quantify the variability and uncertainty of this measured data, this empirical data, considering 95% confidence interval of each empirical EF. And then we, depending on the correlation of these variables that we are taking into account, so we build linear and non-linear regression models. So as I said before, linear regression models can be used, for example, for determining for optimizing the operation of the system in the margin, where really a linear model can work, or in long terms or mid terms application where the margin is no longer the case, we can use a non-linear model that has a computational cost that may be increased. So basically, we got for each individual power plant, we got a confidence interval we are showing here in this slide. So as you can see here, we have 11 plants here that we take around 50 power plants, but we are only showing here 11 plants. So you can see that there is a variability of each individual plant and with respect to the other plants, so not only a variation of the emission factor inside of each power plant, but also with respect to the other power plants. if we, for example, group these power plants in a single one, we may be, in fact, we have a huge more variability. So what we usually do when we model, we simplify the model in order to have a short simulation time. We usually take a group of plants of the same hue. So this can lead to even more variability of this emission factor. Okay? Here we have for SO2 and for PM 2.5. So basically, we also need to estimate, because this emission factor depends on many factors. Some of these factors are the sulfur content, oxygen percentage, and we are based this calculation in terms of these two assumptions, and they are based on mean values of the six power of six of the power plant that we have this information available. So, in terms of comparisons with respect to the SMA and EPA databases of emission factor, what we got in our result is that this empiric emission factor, which are computed for the plant lumped together according to fuel type. So we have coal, we have natural gas, we have petroleum too. We have that basically the empiric emission factor is considerably lower than emission factors provided by this database. So it means that basically when we use this pre-established emission factor from these databases, we are basically being conservative in terms of the estimation of these emission quantities. So, as I said, the EPA recommends that it's better to use a local measurement when it's available in order to have a better accuracy. And we got the same conclusion, because we have quite different emission factors here in this estimation, and we also compute the confidence interval of this emission factor. So, in the case of SO2, it's around one order of magnitude variation between the computed ones and the empirical ones and one provided by the databases. In the case of MP, this is also considerably lower. Okay, this emission factor are also considerably lower. So when we go to in this case for a different results, we can have very similar results. Okay, we have the individual variation of this emission factor for each individual power plant. So we can notice that even for the same fuel source, depending on each power plant, we can have different variations of emission factors computed for both local emissions, SO2 and PM 2.5. Okay, so what does this mean? That it's better to model in terms of emission each individual power plant as a single one and not as a group together. Okay, and in this case, for this kind of source, you can see that even the SO2 emission factor is 1 to 2 orders of magnitude higher than the emission factor retrieved from SMA and EPA. So in this case, it's not conservative with respect to SMA and EPA. In the case of PMs, yeah, it's lower. In this case, so we have lower and rated values. So we need to decide when to be conservative, when to use this emission factor in a conservative way, or when to not use using a conservative. So the correlational analysis of we are only showing here some representative correlational analysis, because not for all the power plants we got this kind of correlation. So depending on the power plant, we found this correlation, but for everyone, this correlation just don't apply. Okay, so we have a strong to moderate correlation of the emission factor for with respect to the power dispatch. So in terms of planning, we were interested in building models that were able to explain how varies the emission factor in terms of the power dispatch, because that's a thing that we usually do when we optimize the power dispatch. So we're interested in computing what is the emission factor for each power dispatch. We also found a positive correlation of the emission factor with respect to the oxygen content. So it means that in terms of the models that we're building to predict this factor, so we are only considering these two variables. So depending, of course, of the model to use, the accuracy of the prediction is gonna improve or not. So for emission factor of SO2, we found this very similar correlation with respect to the forward dispatch. So we basically have a negative correlation, and with respect to the oxygen content, we have in this case a positive correlation. So with this correlational variables, we build some models in order to basically analyze what is the behavior of the emission factor in terms of this power dispatch. Basically, we're building three kinds of prediction models. One of these models are based on linear regression, okay, using the power dispatch as predictor. We were using two nonlinear models. One of them using neural networks, and is based on power dispatch as predictor. And the third one is also based on neural networks, but based on two variables, which are the power dispatch and the oxygen content of the polluting gas cases. So as you can see here, for the linear model, it's not representing very accurate behavior of the emission factor. Okay, we have here the distribution of the error, so it's not a normal distribution. So, but in cases where we are only interested in building planning models where we are working at the margin, where where marginal generators are not changed. So basically, we can approximate the behavior of the emission factor with this linear model, which is the common approach that is used. But as you can see, if we're working in models where the power dispatch varies in a huge degree, it's not at the margin, right? So basically, this linear approach maybe is not reflecting what is happening with emission levels. So in this case, it's better to use a nonlinear model where basically we can represent in a better way what is the distribution of these emission factors in terms of this power dispatch, as you can see here. So we are using planning model, for example, where is considered a time frame of a long-term time frame. Also, we are optimizing the dispatch where the central or where the marginal generator may change. So these nonlinear models can reflect with better accuracy the behavior of the power plant. However, as I mentioned before, this is not the case for all the power plants. Some of these power plants didn't show a strong correlation, as you can see here, with respect to the power dispatch, because as the EPA points out, there are many factors that may affect the behavior of this emission factor. For example, the maintenance of the machine, local conditions, weather conditions. So this is just an estimation that says, okay, we can approximate this behavior of the emission factor for some power plants who behave, who has this behavior with respect to the power dispatch. The mean absolute value error of the multivariate, the case of oxygen and power dispatch as predictor, is between 26 to 85% lower than the mean absolute error of the linear model. So this is an improvement, right, with respect to the linear model. So as a conclusion, we can say that empirical emission factors exhibits a difference between 1 to 2 orders of magnitude with respect to these emission factors that are provided by different databases. In this case, the SMA and the EPA. This means that it's better to have local emissions in order to quantify this emission factor. However, using the emission factor provided by these databases is going to give us a conservative approach in general. Okay? So it depends on the goals that you are trying to do in your model and in your policy, basically how well or how accurate you can you need to do your model. Another thing to consider here is that we are using data from
I'm sorry, time's up.
Okay, perfect. So yeah, that's basically the main conclusion. Thank you very much.
Okay, thank you very much, Mr. Munoz. So, does anybody have a question so we can continue with the next presenter? Okay, so I think that we can continue with the next presenter. Thank you very much, Mr. Munoz.
Thank you.
Okay, let's continue with our session. Our next presenter is Julio Chura from the Universidad Nacional del Altiplano INTERCON. We present the paper number 16 entitled Improvement of Power Quality for Operation of the Grid Connected Photovoltaic Energy System Considering the Irradiance Uncertainty. So, Mr. Chura, the floor is yours.
Are you listening me?
Yeah, I listen you perfectly. Also, I see your screen. It's a little. Yeah, okay. Now I can see your screen.
Okay, thank you. Thank you very much. My name is Julio Chura. I am a teacher at the University of Altiplano Puno. In this moment, I'm going to talk about this paper, Improvement of Power Quality for Operation of the Grid Connected Photovoltaic Energy System Considering the Irradiance Uncertainty. For the introduction of this paper, this research aims to carry out an operational evaluation with an optimal design for the good use of the system and implement it using a 3 kilowatt system of power. In this paper also, we are analyzing harmonic problems at the point of interconnection based on international standards, IEEE, the number 1159, and other is IEEE 519. This is international standards. And in the abstract, we can see the quality of electrical energy for connection to the network is important. Is important when in the university, we won a project. It was financed by the Fondesit World Bank with contract number 118, and with a title, the project or investigation in this part of Peru is the design and validation of the operation and monitoring of a photovoltaic system connected to a network in extreme condition of the altiplano over 308,000, no, 3,800. And the methodology is based on the dependence of the total harmonic distortion on the current solar irradiation. Inverter output currents are AMC voltage for the grid connection points. In the next presentation, we can see how the poor quality aspects of photovoltaic inverters is working. The number one is the photovoltaic technology with MPPT. This leads to the concept of maximum power point tracking, the MPPT. In this moment, in the world, the technologies in the solar technology is growing. It's growing. The intensity of the irradiance varies due to different reasons, such as the variation of the solar incidence time in a day, and atmospheric effects such as the presence of clouds and latitude of the location. Is for that the altiplano is located in a good point. The number two, the MPPT configuration system, the DC stage converted, this current continue, is commonly used for buck booster. This technology, the input voltage level of the inverter, ensuring the acceptable voltage level for startup and the same thing. Its operation range during low irradiance condition. In this figure, we can see how is working the MPPT. We can see the maximum point power and the voltage. How is working the voltage with the current, the short current. We can see the line red is represented by curve PV, partial irradiance, and the blue line is represented by curve IV, partial irradiance. In this part, we can see the point is interacted with current and voltage. And this product, we can obtain the maximum power point. In this slide, we can see also who is working the converter. In this case, is the back boost optional. Who is working then inverter and the filter go to the grid. The source is a power panel for photovoltaic systems. Is in this case the project of Concitec. Concitec was the we can buy the panels and inverters and other technologies. In this moment is the University of Juliaca is installed there. And who is working the MPPT? The most important is the current and the voltage. This variable is working with the panels, and the MPPT is working with the back boosted. Is the main optional technology, and the variable is the power, active power and reactive power. And this is who is working the harmonic in the grid. For example, in these results, we have a voltage of 220 voltage. And also the structure of the single phase, a grid-connected photovoltaic system and maximum power point taking with a MPPT. This is working in this figure. The methodology, this work will analyze the performance of a photovoltaic system connected to the grid. Is regarding energy quality. The system is installed on the Renewable Energy Institute of Energy, the National University of Quebec. And the results with the methodology and the conclusion is working with a photovoltaic system. We have 8 panel photovoltaic monocrystalline, and the maximum electric power is 370 watts peak. Maximum power current is 9.23 amperes. The maximum power voltage is 14 volts approximately. Short circuit current is 9.95 amperes. This is each panel photovoltaics, and total the present study is 8 panel photovoltaic panels. And also for the investigation, we have 8 converters, DC-DC, are incorporated by the grid. In the Solar Edge branch model, for models of 60 and 72 cells in maximum power efficiency, we take at 19.8%, approximately. In this picture, in this figure, we can see who is the configuration, who we have installed in this type technology. We can see the DC and AC protection shield for solar inverter, and each photo panel has his converters, DC-DC, and the results of this paper is the parameters: irradiance, current, active power, non-active power, apparent power, power factor, THD and voltage, and THD of harmonics currents and harmonics voltage, and the maximum irradiance in the altiplano in this part of Peru or the world is 1,000 approximately. It's more than 1,000, and the minimum is 0 watts meter square. The current, the maximum in the part inverter is 8.3 approximately, and the active power in this part was 100, approximately 2,000, 2,000, and non-active power and 200. And the other results we can see in this figure is how is working the solar irradiance when the voltage for the day 10 and 11 October. We have a measurement. We can see who is growing when is the 12 or 10 hours, the day. The other results, the variation of harmonics currents based on the change in solar irradiance. Who is working the solar irradiance? Who is know that the harmonic currents, total harmonic distortion, the currents is growing, is high. The other results, we can see the power factor. The power factor is working with the international law. is IEEE, and we can see is well the power factor depending on the loading of the inverter. In the other results, we can see that type inverter. This type is the Solar Edge 3000, and how is working with the harmonic, total harmonic, and the current. In the figure, we can see output currents and its THD, the currents, total harmonic distortions, both depending on the inverters loading. In this part, we can see the current, how is growing the current with the harmonics. The conclusion of this work in this paper, the objective was the study was to observe the effect of insertion of a photovoltaic system towards the electrical network. For this, the simulation of the output were developed in the inverter. The type of inverter is the Solar Edge 3000, including the converters, the P370 DC-DC, the same one that is installed in the Renewable Energy Institute of NAP. This is a project of Concitec. It was verified that the results obtained meet the criteria established with the energy quality standards for connection to the grid. Related to the work of the MPPT, converters for each photovoltaic modules and uncertainty of the irradiance. This part, it was explained. And the values of power factor varied a lot of during the day. The maximum power factor is 0.9. And reaching desired levels when the inject power approaches the inverter rated power. Therefore, levels of power factor can be reduced by increasing the number of modules photovoltaic, since the inverter use oversights that is the system operated with a power factor capacity, allowing injection of reactive power in the network. Finally, the probabilistic and deterministic approach presented in this study are to determine the optimal levels of penetration of the photovoltaic system, DC and convert on DC-AC. The inverter to the grid under different scenarios for solar irradiation. Lower levels of grid penetration are determined based on power quality parameters that include total harmonic distortion, voltage, current, power factor, and RMS voltage limits. In this case, is 120 voltage. When analyzing the voltage performance, in steady state, it was found that during the operation of the ECT-CR, there was an increase in the mains voltage levels. Maximum voltage remissive is 222 voltage values that are considered critical. Although the harmonics, the current harmonics of the photovoltaic system is very high in condition of low or solar irradiation, and the harmonics and voltage for this condition is lower than with high solar irradiation, and this results currents 19 approximately percent, and the voltage is 1 and 2%. According to the IEEE, the standards, the inverter must supply the electrical network with a current with less than 5%. The harmonic current harmonic when operating at rated power. Thank you, everybody. Thank you very much for the presentation.
Thank you so much, Mr. Chura. So now we can take some time for questions. So you can write the questions on the chat box or on the question and answer chat box. Okay, I think that we have one question, so we can ask this question quickly. I I'm going to write that in the chat box so the question is clearly for everyone. Is the methodology you explained commonly used in business? It's also right in the chat box.
Okay. I think the business of the distribution in this moment very recent now because it's the law, the government of Minister for Energy is not considering in this moment. But in the future, I think everybody, all the world, every the series of the is working for smart grid, no, or smart cities, or the industrial or the factories is buying the panel photovoltaics and they install it the network. In this moment, is studying in other countries and is working, but the government is helping, these countries. But in our countries is depend of the government.
Okay, thank you for your answer, Mr. Chura. And thank you for your presentation. So thanks again for joining us today, and we will see you the next time. Please, we can take advantage of this time to take a break until 12. And the next section is going to start at 12. Okay, welcome everyone again. Thank you for joining us for session 4 of 2020 IEEE INTERCON conference. So for the people that doesn't know me, my name is Erika Pinchi. I am a student at Universidad Ricardo Palma, and I will be your session chair. I would like to remind you to turn off your microphones during this session and type your question to our presenter in the chat in your control panel. I will read the question after the presentation. I also request the presenters to turn their camera on while conducting your presentations and kindly mute your microphone when you are not speaking. So, our first presenter is Reddy Risco from the Universidad de Piura in Peru. He will present the paper number 61, Untitled System Identification Models Fit Using Error Histogram Analysis and the Humboldt Filter as a Computational Tools. So, Mr. Risco, the floor is yours.
Thank you. Thank you, Erika. You listen me?
Yes, I can listen you.
Okay, thank you. Hello, everyone. I will present our paper, System Identification Models using Error Histogram Analysis and the Humboldt Filter as Computational Tools. This paper was elaborated for Daniel Perez, Luis Casaverde, and me. I'm mechanical electrical engineer. We all are doctoral students at Universidad de Piura. Okay. First, I talk about the problem. What is the problem? In the system identification, one type of the system identification is the type black box identification. In this model, is not used now. In this model, we have the input data and the output data, the response of the system. With these two data, we can infer the model of process. We are using parametric models with ARCs or ARMACs. Some of those are the most used for the simplicity. For our work is good. A relevant problem of this type of identification is that the input data can include random noise, white noise, for example, and present outliers. A fundamental aspect of is to identify if what remains on the unidentified part of the model obtained is white noise, or therefore it's not convenient to keep looking for more parameters. It can result in overfitting model. Overfitting model is not good because no generalizes been a good the system. The procedure. The procedure we can using is we found two models, R and RMAX, previously adjusted. We use the function MATLAB function compare is fit and Humboldt compare, which compares the outputs of the identified model with the measured outputs with the validation data. His fit generates a histogram with the adjusted distribution, and Humboldt performs the elimination of outliers using the Humboldt filter. If in the fit output the graph shows behavior close to Gaussian, it allows of the use that the error is already white noise, and therefore is not advisable and not necessary to make further adjustments. After the Humboldt filters is applied, detect and eliminate outliers, we redraw the distribution of the error And if the graph shows a behavior close the Gaussian, similar to the previous case, no further adjustments will be required in the model. This is the procedure. The data set, the present student data set comes from the test bench of 4-cylinder BMW diesel engine, in which 3 data sets had been generated. The data set 1 is data without white noise or outliers. The data set 2 is data with the noise. The data set 3, data with outliers. First step. The first step is identify the best model is to divide the data to identification data. 60%. We have 1,000 registers. We use the first 600 data. And for the validation data, the last 400 data. We opted to obtain a model using ARCs and Armax models with outputs without noise or outlier. This model will be evaluated using the normalized RS and the standard deviation in each resulting parameter. If the model coefficients have remarkably high standard deviation, this parameter should not be considered. This is the results for ARC's model. The error distribution of the base parameters. The error show is similar to Gaussian distribution. This is the results for Armax. Model Armax is similar to Gauss, but no good results. And this is the results of the NRS validation. For ARCs, the fit value is for the validation results 87%, the Armax 68%. But the best model is the ARCs model, and this is the parameters of the best model. Subsequently, validate the result model with the output signals with white noise and outliers. We evaluate the distribution error. If this distribution is Gaussian, then we can consider the error as white noise. The results of this simulation can be seen in the figure. It represents a Gaussian behavior. Therefore, the hypothesis that signal noise of the dataset 2 is white noise is corroborated, and the default model is still valid. With the data set 3 represents outliers. The Hampel filter was applied. You can see in the figure. The first is the original data. The second feature is with the outlier identifier. You can see. We work with the this outlier removed, and we can proceed to validate our model with the filter signal. The results obtained indicate the part of not covered by the model will correspond again to white noise, which is verified with calculate and display histogram error. See the figure. It's similar to original data without outliers, without white noise. Our conclusions of our work is error histogram analysis is useful tool for detecting white noise and avoid over-parameterizing the model, trying to obtain better NRMC. When what remains to identify is not part of the process and the computational tool is using as worked. Likewise, the use of the Hampel filter as a computational tool for the treatment of atypical samples has allowed us to detect and eliminate outliers. The results so that the distribution of the model error related to the validation data after filtering the typical samples was witnessed and therefore prevents us further parameters in the model. And execution pending work is the analysis of the dispersion of parameters. Sync is another user tool to determine if the experiment is being real condition. That is, if the inputs adequately excite the process, if the information obtained is useful for the correct identification. That's all.
Thank you so much, Mr. Risco. Okay, so we will go ahead and take some time for questions. So does anybody have a question? Okay, I think that we have one. How computationally expensive is it?
Not much, because this work is we are using computational basic. Laptop only needs a MATLAB, only necessary MATLAB, no more.
Okay, thank you so much. Okay, thank you so much. So I think that we can wait for a minute until the next presenter is going to present. That it is going to be at 12:20. So if anybody wants to write some other question, maybe they can leave the questions on the chat box, or we have to wait until the next presenter. So let's continue with our session. Our next presenter is Reinaldo Condori from the Universidad Nacional de Juliaca in Peru. He will present the paper number 71 entitled Design, Implementation, and Economic Analysis of a 2.16 kilowatts network connected photovoltaic system SFCR with analyzed microinversor in the geographical and climatological condition of the city of Juliaca. So, Mr. Condori, the floor is yours.
I'm problems with my cam. Only audio.
Okay, no problem. Go ahead.
One moment, please.
Yeah, of course.
Yeah, my name is Reinaldo Condori Yucra. The paper title is Design, Implementation, and Economic Analysis of 2.60 kilowatts network connect photovoltaic system with analysis microinversor in the geographical and climatological conditions of the city of Juliaca. This paper is right at engineer Mari Simbel Wilcachoque and Jose Manuel Ramos Cutipa, me, and Norma Jesus Beltrán Castañón. The resume is this article presents results obtained in the design, implementation, and economic analysis of the photovoltaic system connected to grid with microinverter with an installed power of 2.60 kilowatts, which are being analyzed in geographical and climatological conditions of the city of Juliaca, localized in highland region of Puno. The photovoltaic system is installed in the National University of Juliaca, UNAG, in Ayabaca's headquarters. It is made up of 18 photovoltaic modules of 270 watts, model TP660P, and 8 microinverter with output power of 215 watts, and on the fast M215 model is a protection system. The photovoltaic system is a 2.16 kilowatts generating power. Is a little introduction. Throughout research the development group in solar photovoltaic technology, grid solar of the National University of Juliaca, NAG, is in Juliaca. It participates in this project, design and validation of the operation and monitoring of grid-connected photovoltaic systems. In extreme conditions of the altiplane over 3800 meters level of the sea. This is materials and methods. An overview installation. The installation of the photovoltaic system is located at the roof of the Renewable Energies and Energy Efficiency Institute of the Professional School of the Engineering of Renewable Energies, Pierre Ayavaca's headquarters. It is located between the geographic coordinates of south latitude 015 grades to 0.59 as the west latitude 70 grades and this detail view. The photovoltaic system consists of the 8 polycrystalline Celesum model TP660P brown photovoltaic modules with a nominal power of 270 watts and 8 microinverters en phase of model M215 rate output power of 215 watts. Its materials view the altitude, the Juliaca, methods is the superstructure for a photovoltaic system was designed and monoposed and there will be 8 these structurals with a mobile support to able to vary the inclinations of the 8 photovoltaic modules and they capture as much radiation as possible. The structure was made of galvanized steel in the order avoid corrosion due to the climatic condition of the city of Juliaca, very cold. The design of the superstructure should facilitate the installation and maintenance of the photovoltaic modules NTP M080 in figure 1. Its short design support structure was used photovoltaic system oriented of geographic north and the inclination of 15 grades. The design was made using the AutoCAD tool of the monopost type support. View figure 1 is at a single post. Materials and methods. Recommend voltage drop limits is 1% to 3%. With the help of equation 1, we will obtain a minimum sector of the conductor of CI, depending of the length of branch, the nominal voltage of the level loss. Where resistivity of the conductor material generally cover cover is good. Total driver distance, current passing throughout the conductor. Tolerate voltage drop in the wire 4 millimeter section was selected. The EUSA brand Newark thermomagnetic switch with the capacity of 15 amperes protect electrical equipment and conductor caused with short circuits and electrical overload. This is a view, the figure 2, the single line. But diagram SFB so wrong. The net present value internal rate at final the investment recovery time are calculated. This parameter will be calculated now investment of the photovoltaic system in the order determine the economic parameter. And the investment of voltaic system is one of us essential that to determine the viability of a research project in the table 3. This case, table 2. We have set of the approximate budget. We are doing the details, the equipment, usage of installation of the photovoltaic system connected to the grid with a microinverter. See table 2, essential parameters to evaluate the economic analysis. Table 3, C, and book it the photovoltaic system with a microinverter. The name of description, units, quantity, the price is subtotal. With the price, the materials, protections, drivers, grounding, transport, welding, at the total the cost is the project is the figure the panel solar it is a structure. Results for the electrical design of the photovoltaic system connected to the grid with a microinverter. The multi-wire diagram is designed showing the connections detail, which indicate that the conductor of the CI site have a following measurement. The neutral phase conductor is 4 millimeter, and the grounding conductor is 6 millimeter. As well as a general panel, we are meter and the protection system are localized to later be connected to the low voltage power grid. Puno is one of the departments with the highest solar irradiations, since it be verified with a study that of the night. The irradiations data were measured an inclined plane of 50 grades. The data we are taking in a period of 1 year with often night. The average of irradiation is 5,984 kilowatts hour over meter. And finally, the shadow simulation was carried out to the SketchUp, where the photovoltaic modules were placed with a separation between modules, and the result was 1.15 meters of separation, drop separation, in between photovoltaic modules, was found at the voltaic system, so this does not present shadows. Therefore, the system is the suitable location. Conclusions is the conclusion which was a successful design. The system photovoltaic has was using the tool program AutoCAD. Is the system have 8 modules photovoltaic and 270 watts and 8 micro inverters. Analyzed BPM does result the for 773.83 sols months in a Peruvian money, and was tier with 19% peer and peer with 5.62 years. This is all. Thanks.
Thank you so much, Mr. Condori. So we have some time to take to write some questions. So if anybody have a question, please write on the chat box or on the question and answer box, please. So let's give some time to write your question. Okay, I think that we have one. So it is in the chat box. It is. How easy is to implement photovoltaic systems?
Yeah, these easy installations for photovoltaic module with little problems with temperate ambient. This all. It's all.
Okay, thank you so much, Mr. Condori. So if anybody have any question, we can wait until the next presenter that is going to present at 12:40. So I think that we have to wait a minute. Okay, continue with our session. Our next presenter is Alex Guzman from the Universidad Nacional de San Agustín de Arequipa in Peru. He will present the paper number 131 entitled Small Signal Stability Analysis of Power System of Arequipa using PSAT. So, Mr. Guzman, the floor is yours.
Okay, thank you. Thank you for being here today. My name is Alex Guzman. I am a graduate student of electrical engineering. I would like to talk to you about small signal stability analysis of power system of Arequipa using PSAT. Well, topics. There are four essential definitions that you should know: small signal stability, PSAT, eigenvalues, and the Lyapunov method. Small signal stability is defined as the ability of a power system to maintain synchronism when subject to small disturbances. PSAT is a toolbox from MATLAB for the analysis and control of power systems. Eigenvalues are the roots obtained from the characteristic equation of the state matrix. The Lyapunov method is a method which allows us to determine the stability of a system depending on the eigenvalues. Well, in simple words, small signal stability is a special ability of power systems. PSAT is an external complement from MATLAB. The eigenvalues are complex numbers that we get after simulating the power system chosen. And the Lyapunov method gives us three conditions to analyze if the power system has small signal stability or the ability to maintain synchronism. Well, the problem. Actually, doing this analysis without any computational tools is a laborious process. But also the training to students about this topic is difficult. Well, fortunately, there are some softwares that simplify the implementation of small signal stability analysis. However, many of them are paid software. So why was PSAT chosen? Because PSAT is a free alternative. But someone could say, yeah, PSAT works with MATLAB and MATLAB it's paid. Yeah, but happily, MathWorks offers the campus-wide license that provides unlimited use of MATLAB and Simulink products to faculties, research universities, and researchers. The other reason to choose PSAT is that PSAT provides some functions like power flow, optimal power flow, aging analysis, and others. Why was Arequipa power system chosen? Or why was a real power system chosen? Well, it shows that the use of a real power in our research is not difficult, and demonstrate that the local research is possible and necessary. So this article shows an alternative to students for doing this kind of analysis in a simple way. The methodology. Well, the first step is to choose the power system. In our case, it was Arequipa's power system. But how did I get its data? Well, COE's website provides us with the entire SAIN data. However, Arequipa's power system is a little part of the National Interconnected System, or SAIN. So Arequipa's power system had to be isolated using an external grid and equivalent loads. The next step is to make the graphic representation. If you see, is there the graphic representation of Arequipa's power system. Some information about it is it has 70 generators, 40 transmission lines, 57 bus bars, and there are colors that represent the voltage levels. In this case, the light blue represents the 138, yellow represents 33, and green 10 kilovolts. Before the results, when you make your graphic representation, you do the aging analysis. But you need to perform the power flow analysis. In that case, the power flow analysis in PSIT provides us some results like voltage, angle, active power, reactive power, and the state variables. Those state variables are the rotor angle, rotor speed, and flow links. In our case, rotor angle is delta, rotor speed is omega, and flow links is represented by E1Q plus the name of the generator. The second picture shows the values of voltage. In our case, there are 3 particular values, but this picture don't show which bus bar it is. Well, an important step is the small signal stability analysis. PSIT provides us the graphic of all aging values. These aging values give you in a report, show you in this table. If you see, there is a particular feature of aging values. All aging values have a negative real part, but how it means? Well, according to the Lyapunov method that gives you 3 conditions, if your all aging values have a negative real part, means that Arequipa's power system or your power system has the ability to maintain synchronism even though small disturbances appear. Another conclusion is about the 3 particular values that you see on the last picture. If you're checking deeply, these 3 particular values are from INTERCON bus bars. So it means that the INTERCON bus bar works close to the limits of voltage. Thanks to these results, PSIT tool has proven to be an excellent complement to the design and analysis of electrical power system. Thank you, and we can start with the question and answer session.
Thank you so much, Mr. Guzman. So as Mr. Guzman said, we can start with that time for questions. So if anybody has a question, type on the question and answer box or on the chat box. So we are going to wait a few moments.
I sent a question in the chat box.
Oh, thank you. I couldn't see that question. I'm sorry. Can you say the question orally, please? Because I couldn't find the question.
Yes, I would like you to know what's the main participation of the colleague Alex Guzman in this research or paper, and what's the major, the greatest difficulty in producing these results.
Well, I said that the reason for this paper is to show an alternative to students for doing this kind of analysis or small signal stability analysis in a simple way. You just use software that provides you a simple way to do that and shows the results of Arequipa power system, and it means that Arequipa's power system has the ability to maintain synchronism. And that's all. You have another question, or you need more explanation, maybe?
My question is about your participation on the paper.
Well, my participation. How explain that? Let me think. Yeah, according to the conclusions, we conclude that the PSAT is an excellent software to do this kind of analysis. Because you see some results about the aging value analysis. PSAT proves many results about power flow, about aging value analysis. And you can analyze them to conclude if the power system chosen has the ability or not, or if you need to analyze deeply this power system.
Okay, thank you so much. Good job.
Thank you.
Okay, thank you so much, Mr. Leal, and thank you so much, Mr. Guzman. I'm really impressed about you are the student. Well, me too, I am a student, so it's very nice to listen that anybody is that any student is participating in INTERCON now. So thank you again for joining us today. We will see you next time, and I hope you will have a good day. Continue enjoying the next sessions now. Thank you so much.